For this one, we have another molality question. As a reminder, molality is the kilograms of the sol. Oops. It's the moles of the solute divided by the kilograms, or the mass, of the solvent. Just don't get that mixed up with molarity. They're very similar words. Even when I think about them, I get them mixed up. I just have to stop and think a little harder about it. So, with this being said, we're basically looking at converting one type of concentration or quantification to another one. If this solution of methanol is 25% methanol by mass, that means that there are 25 grams of methanol. Okay, how am I going to write this? Doesn't matter. CH3OH. There's 25 grams of methanol for every 100 grams of the entire solution. That's for the methanol. You always have to think about what's happening on the other side too, and that means that for water, the rest of the solution's got to be water. There's 75 grams of water for every 100 grams of this aqueous methanol solution. That's going to be important. I'll put this one away and we'll come back to that one. Let's just deal with this part now. Actually, I'll put both of these away because these are both small pieces. You're going to end up using dimensional analysis, but you really have to think about what you're using it for. So I'll change to green and see what's going on here. So let's see. To convert, we want to see, well, let's just assume we have a 100 gram solution. We have 25 grams of methanol, because this is just a ratio anyways. If you have 25 grams of CH3OH, let's just convert our grams of methanol into moles of methanol. And you'll see why that's important, because it is the solute, so that's going to be our numerator here. So grams to moles. We have that 1 mole of methanol is 32.04 grams. Convert, and you get, well, how many moles is that? And that's going to be, I don't know off the top of my head, obviously, so let me pull out my calculator, 32.04. 0.78 basically. Now that's going to give you the numerator part. That's great. Move on though with the bottom part. What about the kilograms of the solvent? How do we find the kilograms of the solvent? Well, the solvent is water. Water is called the universal solvent. So we can just replace that with H2O if you're confused on solution, solute, solvent. Make sure you know those 3 S words. So the solvent is what is the main bulk of it typically. It's what everything's dissolved in. So we're gonna have to use this information. We have 75 grams of water. Convert that from grams of water into kilograms of water. And then we have that 1 kilogram is 1,000 grams. Do your math. And then you're gonna get 75 divided by 1,000. That's 0.075 kilograms of the solvent, which is water. Then you just divide. So to do that, you take this number and you divide it by this number, kilogram H2O. And that's how you get the molality, which is going to be your answer. So that's what your answer is this. I'm going to just double check and make sure with my own calculator. Divided by this. Yep, we get 10.4. This answer here is a really good distractor because it's very common for people to want to convert 100 grams of the solution and make it 1,000, basically you're not converting this 100 grams into kilograms. Remember that for mass percent, some percent is one thing, and the rest of it is usually typically going to be water. For this question, it says the vapor pressure of water is at 26 degrees is 25.21 millimeters of mercury. You can think of this as being the pure, so to speak, or the standard pressure at that particular temperature. So we're going to call the water, let's put H2O here. Okay, so that's the reference you can think of it as. But because we're dissolving something in this water, the vapor pressure is going to decrease because it's going to make it a little harder for those water molecules to escape into the gas phase. So the vapor pressure of the gas above the water in the solution will go down. So this equation is going to be the one you're going to reference. That is going to be the pressure or the vapor pressure of the water. It's going to be equal to the mole fraction of the water times the reference pressure, so to speak, at that particular temperature. So it means we got to find the mole fraction. As a reminder, mole fraction is just moles of the one thing divided by the total number of moles. So the first step is to find your moles of glucose given the grams of glucose. That's super easy. We know how to do that by now. So 20 grams of glucose, convert that from grams of glucose to moles of glucose. 1 mole is about 180 grams, and we get 20 divided by 180. And that's 0.111 moles of glucose. Now that means we have the numerator, we have one part of our mole fraction. This solution is mostly water, so the mole fraction is going to be a relatively high number. So right now, as a reminder, we're calculating the mole fraction so far. Then we also have the water. So we have 70 grams of water, 70 grams of H2O. I can convert my grams of H2O to moles. Obviously, the molar mass is given to us as about 18.0. And when we do our math here, we get that 70 grams of water is about 3.889 moles of water. So it's easy to see how many total number of moles there are. Just add these two things up. So mole fraction is moles of one thing divided by moles of another thing. So in this case, the mole fraction is going to be referencing water. So that's going to be this. The mole fraction is 3.889 divided by the total number of moles, which is 0.111 plus 3.889. And when you get a mole fraction that's large, let's see, about 0.972. Get rid of all of this, because that was just converting grams into moles. And what we have so far, let's move this way, is that the mole fraction is 0.972. Basically saying it's almost all of the moles of the solution are water, and that makes sense. And their reference pressure is 25.21. So you do your math and you get your answer. 97.2% of 25.21 is going to be what that is. 6 says Henry's law constant for carbon monoxide and water is, or at that temperature, is 9.71 times 10 to the negative 4. How many grams of carbon monoxide would dissolve in 1 liter of water at the partial pressure is 2.75 atm. For this one, it's a Henry's law problem. And even if you don't really remember what the equation is or whatever, this is a great example of how dimensional analysis is important, because you look at the units here for this constant, and it's really written out like this. It's moles divided by liters times atmospheres. And if you think about how to get rid of everything, you have liters, so you can multiply that by liters over 1, so that gets rid of it here. And you also can multiply it by atmospheres, because you have ATM over 1, gets rid of it here. If you do that, that basically tells you, well, kind of like how you kind of like can BS questions, right? Just multiply this constant by this, by that, and you end up getting some small number. You get 0.00267 moles of CO. Now, of course, we can convert our moles of carbon monoxide into grams of carbon monoxide, which is what it's asking for, by just recognizing that the molar mass of carbon monoxide is 12 plus, like, 16? What did I multiply? Yeah, 28. And then that gives you your answer. All I did here was convert moles into grams for carbon monoxide. This one says, which of the following aqueous solutions will have the lowest vapor pressure? The answer to the one that have the lowest vapor pressure will be the one that creates the most ions. So the more ions there are in the solution, the lower the vapor pressure will be, which basically means that the water that's part of that solution will have a harder time escaping to the gas phase, and the pressure above that solution will be lower. So you really just got to know your ions, really. And also multiplying by this value here. So AlCl3 would create 3 ions. Nope, 4 ions. And this is assuming they all completely dissociate. So 4 ions. H2SO4 will create 2 H ions and sulfate ions. So that'll be 1, 2, 3 ions. And again, we're assuming they're completely associated, which is not necessarily reality. MgNO3, so magnesium nitrate, will create 3 ions. NaCl will create 2 ions. And then this is glucose, which creates no ions. Now, although it creates no ions, it does create 1 particle. It's going to just remain what it is. So you can think of these as like the I value, so to speak. Now, don't forget you have to multiply those values by the concentration. So 4 times 0.50 gives us just 2. 3 times 0.6 gives us 1.8. 3 times 0.75. Don't know why that one's not going to go in my head right now, but let's just see. 2.25. So 0.75 gives us 2.25. 2 times 1 just gives us 2. So 2 ions times the concentration of 1 gives us 2. And then we have 1 times 1 gives us 1. So the reason that this is the right answer is because not only does magnesium nitrate create the most, well, it doesn't create the most ions, but it has the highest concentration once those ions are all dissolved. So again, find out how many ions they make. Recognize that molecular compounds or covalent compounds are not going to make any ions. They'll stay just 1 particle. They'll dissolve but not dissociate any further. And that they just multiply the 2 and you figure out which one has the highest amount. Number 8, it says, in which of the following pairs of compounds is the compound that is likely to be more soluble miscible in water listed first? Ugh, that's a lot of words. So, looking at this, we have, carbon tetrachloride and methanol. Well, water, you may have heard the phrase like dissolves like. So, especially if you're going to like some kind of health profession or whatever, you just need to recognize like solubility and such, and that water is going to end in H2O. So it's going to relate it to like intermolecular forces, hydrogen bonding. Water can hydrogen bond because if you look at the structure of H2O, it has hydrogen connected to an oxygen. So there's some kind of electron density unfairness, so to speak, which means that this is going to do hydrogen bonding. So you're looking for something that can do hydrogen bonding. So let's first of all recognize that something that's going to be more likely to dissolve in water will have OH, typically, if we're talking about molecular compounds. So we want it to be listed first. This one is not going to make sense because methanol is going to dissolve in water better because it has an OH, but it's listed last. So that's not a good one. Methanol versus pentanol, it looks like. Now you have 2 things that have OH. So once you have 2 things that have OH, you want to pick the smaller of them because all those extra carbons and hydrogens are not going to be very easily soluble or attracted to parts of the water. So when you have 2 things that have OH, pick the smaller one. The more carbons there are, the less likely it is to dissolve. And that's actually the same logic behind why the right answer is right. OH, they both have OHs, but this one has so many extra carbons that every extra carbon makes it less and less soluble. Which of the following solutions exhibits dipole-induced dipole as the principal intermolecular force? So that basically means we're looking for something that is not going to do hydrogen bonding because it's not, that's a bigger intermolecular force. We're basically looking for something that can only do London dispersion or van der Waals forces. So it says dipole-induced dipole. You really need to think of this as 2 different things. Dipole and induced dipole. Dipole means that it's going to be polar. So one of the two things has to be polar. Water is polar. So we've got water, water, and water. So far we have the polar part. Now, when it says induced dipole, that means we're looking for something that is not dipole, that is not, that does not have a dipole on it. So nonpolar. This methanol is polar, so this doesn't, that would be dipole-dipole. If you dissolve methanol in water, you have a polar thing and a polar thing. So because methanol is polar and water is polar, that's not the right type of relationship. Skip down to the third one. We have NaCl, that's going to dissolve, or at least it would try to, but it's not going to really dissolve in CCl4. So the reason that this one's not right is because, first of all, CCl4 is not polar, and the NaCl is an ion. It would become an ion. I2, so iodine is nonpolar, so that works so far. But so is the C6H4, which I think is hexane. So because these are two nonpolar things, that's not going to work. So let's go back and actually label it probably a little clearer way. This would be polar, polar. Not what we're looking for. Skip down, that would be ion, and then nonpolar. So it's not even going to dissolve. Then the fourth one is going to be nonpolar, nonpolar. And then the last one's going to be ion polar. The only one that makes sense is the fact that O2 is nonpolar, so that takes care of this part. And then water is clearly polar, so that takes care of this part. It's got to know your IMFs. For this one, you got to recognize that we have LiCl here. Lattice energy is an endothermic type of, you can think of it like endothermic in terms of it's going up. And it actually says it right here, 834 kilojoules per mole. So that's this part. Then it reaches the part where it is dissolved, but then we have the heat of hydration, which goes down. And this one goes down by 871, so it's going to go a little lower. So negative, that's why it's exothermic, 871 kilojoules per mole. So you're looking for this little difference here. And that's really easy to calculate. That's going to be really just 834 plus the negative 871, and you get negative 37. Negative 37 kilojoules per mole. And just as we've seen a million times, is going to be good for our dimensional analysis. Negative 37 kilojoules per 1 mole related to LiCl. So convert your moles into grams of LiCl. And now look at that. We actually have the molar mass to do that conversion, which is easy. 1 mole of LiCl has a mass of 42.4. Now, if you look at how your units cancel out, oops, that should be flipped. Move that down. Perfect time to check. That's why I literally still cancel my units out, even though I know chemistry. It's because mistakes are common, so I just cancel those out. Perfect. Now, continue on with your math. You have grams in the denominator, put grams of LiCl at the top. And you can actually just call it off there because you want your answer to be in kilojoules. You want kilojoules to survive. You want everything else to die. And that's what's going to happen here. So you have 16 grams of this. And basically what I just did was I converted 37 kilojoules into grams using the molar mass to get it into moles, and then using that 16. So all of that to say, that's going to be your answer, 37. Of course it can't be negative, so you can really mentally get rid of the negative, because you can't have a negative, it's just asking about the amount of heat absorbed or evolved. Because you end up getting a negative answer and you don't see negative here, don't freak out. That just means that the heat is being evolved or given off exothermically. So this one says, which of the following lists the molecules in order of increasing miscibility or solubility in water? We saw earlier with the intermolecular forces. Basically, the trick is this: when you think about water, you want to see hydrogen bonding for something to really be dissolvable. So hydrogen bonds are good. If you see OH, that's great. If you see other things like lots of carbons, like lots of CNHs, that's not good. Also think about geometry. I think you probably learned in the prior semester of chemistry about polarity and geometry. Something that is going to be have the same atoms all around is going to be non-polar. So this would be like CCl4. So take a look at things that have OHs are going to give us high miscibility. So we want that to be on the right. So that's going to be things like methanol and methanol. Okay, actually, this is a relatively simple question. Now, things that are not going to be highly miscible, you want things that are going to be like things that have lots of carbons, or they have carbon surrounded by 4 identical atoms. Those are going to give you very, very non-polar things. So things like CCl4, very non-polar. And then you have ones that are in the middle. Trichloromethane, which is this, has some polarity, but it's not as polar as it could be. That's why this is the answer. This question says, in each of the 4 graphs, the solubility of a particular gas... What? Oh, okay, let's try that again. In each of the 4 graphs shown, the solubility of a particular gas in water as a function of pressure at 25 degrees Celsius is shown as a solid line. Choose the graph with a dotted line that would describe the solubility of the same gas as a function of pressure at a higher temperature. So when temperature goes up, solubility goes down. So as this one's a little tricky, you kind of just have to read it really carefully. It says the solid line is the normal. So that's normal, that's normal, normal, and normal. And you just have to remember the rules about solubility when it comes to gases. Think of this as like what happens with soda. If you have a cold soda with the top open, it will not go flat, which means the carbon dioxide gas will not come out easily, compared to a warm soda. Warm sodas go flat faster because gases don't dissolve as well in warm solutions. So you're looking for, because this is higher temperature, you're effectively just gotta remember the laws and the rules about it. You're like, oh, higher temperature means less dissolving. So which of these dotted lines represents a lower solubility due to the fact that it's a higher temperature? It's not instantaneous. It is linear. So basically, the higher the temperature is, the bigger the gap. So that's why this is the right answer. Like a small temperature, like a small little decrease in temperature, not going to cause a massive change. But as the temperature goes up and up, the solubility starts to decrease even more. And that's why that gap widens. Number 13, what is the mole fraction of water in 20 grams of 95% by mass ethanol? So a lot of this math stuff can be really confusing because you have all these different concentrations to think about. Remember that mole fraction is simply equal to the moles of the thing you care about, so in this case water, because it says the mole fraction of water, divided by the total number of moles, which is going to be, in this case, the moles of H2O plus the moles of ethanol, which I'm just going to write as ETOH. Now, we can always make a couple of assumptions about, because they're ratios, you can play around with the numbers as long as you don't break any rules of math. So since it says there's 200 grams of 95% by mass, what that really means is if there are 200 grams of solution, then 190 grams of that solution are the ethanol. And that's because, of course, if there's 200 grams of it, just take 95% of 200 and you get 190 grams. And that also means that, well, clearly the remaining 10 grams of missing mystery stuff is the water that the ethanol is also with. So 10 grams of water out of the 200 grams of the solution. So that means you basically need to take 190 grams and convert it to moles. Take your 10 grams and convert it to moles by just doing your dimensional analysis. So let's do that with the ethanol. 190 grams of ethanol. If I convert that from grams, from grams to moles, I'm using this molar mass here, of course. I get, let's see, 4.13 moles of ethanol. So moles of this. Now if I do the same thing with the water, I take my 10 grams of H2O and convert it from grams to moles. We know that 1 mole of water is 18 grams. That gives me 0.55, really 56 moles of water. So I just found the moles of ethanol and the moles of water, and then I can just plug those into my equation. So for the moles of water, I clearly am going to put this here. So duplicate, and that's in the numerator. And I also need that in the denominator. Whoops. So that's going to be duplicate, and it's going to go right there. Let's see. That was not as pretty as I wanted it to be. There we go. And then, of course, for moles of ethanol, get rid of this. And we're going to put this in there. And then you got your answer. Okay, my battery is apparently running low. And that's why you have such a small amount, because the vast majority of this is ethanol, and that's why you get this answer from. So it says, what is the strongest type of intermolecular force between molecules of SO2? So you probably want to draw out SO2 because it looks very much like CO2. It looks kind of balanced-ish. But you got to learn, or remember, I should say, how to do Lewis structures. So SO2, which has a sulfur, is in the, actually they're both in the same column. So it's going to be a total of 12 valence electrons. So I put S and then the O. That's not 12, 18. Because they're both in the 6th tall column. So they both, S and O have 6 valence electrons each. That means I have a total of 18 valence electrons to use in my bank. Connect them once, and I just used 4. That means I have 14 valence electrons remaining to put around the edge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. In order to get this to actually be balanced, we want a double bond in there somewhere. If remember how this looks, this is basically going to start off to have a trigonal planar electron region geometry. But after all is said and done, you have a lone pair above the S, you have a double bond and a single bond on either side. And all that to say, this is a polar molecule. You have to kind of look back to how chemistry, your first semester of chemistry worked to remember that this is polar. If there are a lone pair on the central atom, and that central atom has 4 or 3 electron regions, it's going to be polar, and that's why dipole. Dipole is stronger than hydrogen bonding. Plus, this can't even do hydrogen bonding. It doesn't have any hydrogens in it. This one says urea is a non-volatile non-electrolyte. Non-volatile means it does not evaporate very easily. Non-electrolyte means it's not ionic or acid or base. It's covalent. And it has a molar mass of 60 grams per mole. If 30 grams of urea is dissolved in 200 grams of water, what is the boiling point of the solution? We are coming back again to the boiling point elevation and freezing point depression. So in this case, it's boiling point elevation. We have I, M, K sub B. Remember that for non-electrolytes, I is equal to 1. So we can just put a 1 there. And the molality, we don't know the molality, but we can find the molality. So step 1, find the molality given this information. Remember that molality is equal to moles of the solute, in this case moles of urea, divided by the kilograms of the solvent, which of course in this case is going to be water. So how many moles of urea are there? Well, urea's molar mass is given, so we can take our 30 grams of urea and convert from grams of urea to moles of urea. And it makes sense that 1 molar of urea has 30 grams. Oh, sorry, 60 grams. So 30 divided by 60 is equal to 0.5 moles of urea. That means we're going to replace that in our numerator. 0.5 moles of the urea. To find the kilograms of water, it says it's dissolved in 200 grams of water, which is 0.2 kilograms of it. I just turned, if you want to see how it works, just 200 grams, divide that by 1,000, and you get 0.2 kilograms of H2O. That gives us a molality of, I think, 2.5. 0.5 divided by 0.2, yeah, 2.5 moles per kilogram. That is the molality you need to put up in this equation. So if you slide those open and then get rid of this, we have now found a molality of 2.5. And then we are given, of course, Kb, which was 0.512. Multiply everything to this times 0.512. And we have a change in temperature, so delta T, that's going to end up being 1.28 degrees Celsius. And of course, you just tack that on, because remember, this is the change in temperature, so the boiling point of water is 100. It goes up by 1.28, which is why the answer is 101.28.